Hello. Today we're going to discuss a little bit about organocompounds, but particularly, we're going to talk about bioreactors and their behavior before and after fermentation. So, organic compounds are related to that because organocompounds are part of what's the feed in a bioreactor. You maybe put in an organocompound. It has maybe a carbohydrate such as glucose, which is an organocompound. It has an organic branch, and you put in a microorganism. You supply air and you supply other parts, or for example nitrogen, you supply magnesium, you supply iron, you supply calcium, basically these nutrifying elements that can help the microorganism consume the substrate, in this case which is glucose, and basically form a byproduct for Saccharomyces cerevisiae, which is a microorganism used in fermentations. When you're making an alcoholic drink, the byproduct is ethanol, which is also called ethyl alcohol, and this byproduct is what's responsible for the alcoholic content in an alcoholic drink. It is the main component or byproduct, for example, in an alcoholic drink. So there you have it. A bioreactor reacts these nutrients, and the substrate is glucose, and then you have two types of bioreactors, maybe three types. You have a batch reactor, which is there's no continuous input and continuous withdrawal of byproducts. It's a batch reactor where you place the microorganism, you place the substrate, you place the nutrifying elements, and there's the reaction, and once it's done you take everything out. So as you may have guessed, this has its advantages, where you have when you're taking everything out, there's very little chance that you're going to get contamination because the system is closed, and so there's no new introduction of the species. There's no contamination. There's no everything is controlled. The molar concentration remains constant. You have mainly a controlled, closed-off system, but the disadvantage is that maybe there's not enough. You get it's not very efficient in terms of the time that it takes and the effort as well, and maybe might also increase the cost just because you're having to stop and start the reaction for different time intervals. The second one is the semi-batch, or as well known the fed batch, and this is where there is a continuous feed, but there's no continuous outlet. So continuous feed, you're supplying the nutrients, the oxygen, the aerobic components, and they're reacting as usual. There's kind of denitrification, there's oxidation as the bacteria consumes the elements to make its byproduct. Maybe they're non-photosynthetic organisms. Many reactions take place. Heterolytic cleavage, where you get these radical atoms reacting in the mixture, and they can be these bacteria are heterotrophic, so they depend on they can photosynthesize, they can recreate their own carbon source, but they do need some elements. They don't need an organic source, but they do need carbon dioxide to create nutrients for themselves and grow and reproduce, because bacteria reproduce by fission, budding, where they split their cell walls and form these kind of new cells. Out of one cell divides into another, so they don't need to. It's an asexual reproductive mode. So the last type of reactor, bioreactor, is the continuous reactor, continuous feed reactor. And this is where you have the reactor is an open system. There's a continuous feed, there's a continuous output, and in this reaction you can do a mass balance, and you will see that indeed when there's a continuous feed you have chance for contamination, but since the variables are controlled, for example pressure, temperature and volume, you will have a better chance of producing more in a short amount of time, just because of the flow is continuous. You're not starting and stopping the process. The flow is very maybe it's usually a laminar flow. There's a piping, it's a laminar flow, and you have all these nutrients coming in, excretory products. You have maybe productions of excretory products from the microorganism. You have the substrate being consumed. Now when you plot a substrate cell population or concentration of substrate, or maybe it could be the cell number as a dependent variable and time as the dependent variable, you will get a curve that is determined by a polynomial, and that curve will have a few phases. It will have the lag phase, it will have the accelerated growth phase, which is also the exponential phase. It will have a phase where the curve kind of sticks out, so that's the kind of the slow, the decline phase. And then you'll have the steady phase, the fourth phase, and then you'll have the stationary phase, the steady phase, the stationary phase. You'll get the death phase. So the death phase is a part where if you took the derivative of the curve, if you drew a tangent line to the curve and it was a best fitting line of best fit, and then you took the derivative, the slope of that tangent line, you would get a negative number, because the rise of a run, the decline, the rise of a run would give you a rise of -1 or -2, -3, whatever, over a positive run. So a negative number divided by a positive number will definitely give you a negative number, so the slope will be negative. So that's the last kind of type of bioreactor. So let me know what you think about these my explanation into this particular topic, and leave a comment, subscribe to my channel, and don't forget to like, comment, and subscribe, and share this video to other people that are going to watch it. Thank you very much.